let's go ahead and get started. Let's see. I can pick up from last time. I have finished grading your numerical solution, that 1.50. I just forgot to bring it with me, but they were good. That's all I gotta say is everybody did a good job. I'll bring those next time. Another thing about next time is I think that there's a homework assignment due next time. All right, thank you. So please keep that in mind. Before we get going, are there any other questions or anything else we should discuss? All right, then let's do it. Okay. So last time we were talking about Keplers laws. I apologize. I didn't have any caffeine today, so I'm dragging a bit. All right. And so Kepler's three laws were that planets move in ellipses with the sun at one focus, planets sweep equal areas in equal times, and that the period of planets' revolution squared is proportional to their distance, well, their length of their semi-major axis cubed, would be the better way to say it. So let's go ahead and talk from there, because what we are going to do is we are going to prove Kepler's first and third laws. They all come straight out of Newton's second law. We're going to prove the first and third in chapter 8. We're going to go ahead and do the second now. So Kepler's second law. As each planet moves around the sun, a line drawn from the planet to the sun sweeps out equal areas in equal times. Okay, so that says that the planet moves around the sun, a line drawn from the sun to the planet sweeps out equal areas in equal times. That's Kepler's second law. It also applies to comets and anything else moving around the sun. And another way to state this would be to say that the time rate of change of the area swept out is equal to a constant. All right, that says constant. All right, so and what that's referring to is, so we have some sort of an orbit here. Here's the sun. Here's the planet. During some increment of time, it sweeps out that area. Maybe over here in an equal increment of time. Those two areas are supposed to actually look kind of the same, but okay. All right. So nonetheless, if this is the in some sort of incremental time period, we could note that this area here would be the incremental area swept out, all right? Then our expression for that would be, well, we've got r here, which is the distance to the planet from the sun, times, and here's the velocity of the planet, times dt. V dt, actually that I don't want that as a vector right now, it's just drawn on there. And I see that I can make a triangle. It could have its base be r and one of its sides be v dt. and its area would be 1/2 r cross v dt, where v dt would be a vector in what I just said. So it would be 1/2, sure, let's go ahead and make them vectors after all. So 1/2 r cross v dt, just for the area of that triangle. Are you guys okay with that? All right, cool. All right, so what I have is dA dt, which also must have a vector. We'd have to ascribe sort of a direction associated with dA. That's okay, we can do that, that's fine. Its magnitude would be 1/2 times the magnitude of r cross v. That should be magnitude sign. I'll put an m in there, an m down here. 1/2m times the magnitude of the angular momentum of the planet, which I know doesn't change with time due to a central force. So in this case, I know for physics reasons that L must be a constant, and therefore the time rate of change, the area swept out by that object, is also a constant. So I'm going to go ahead and note that we'll just say since L is measured relative to the sun, and the sun only provides a central force, L is constant due to central force, which in this case is a gravitational pull, then dA dt is constant. I think that I'm ready now to just go ahead and call that a QED. So Kepler's law, Kepler's second law will always hold for objects moving under the effect of a central force when when we're talking about with respect to the object that is providing the central force. All right, so because that's what we're talking about, this area being swept with respect to. That's also what this angular momentum is calculated with respect to. All right. All right, so we'll say that that is proven. Okay, are there any questions about that? Cool. Now let's move on. Sure, angular momentum for several particles. So I'm now going to have a system that consists of n different particles. And I want to talk about the total angular momentum of the system. Okay. So in this case, I'm going to consider n particles. And I'm going to go ahead and let my counter be alpha. And each particle, therefore, has an angular momentum, which will be represented, since it's for a single particle, with a lowercase l of r cross p, where r is measured with respect to some origin that we've chosen. Okay. So in this case, the total angular momentum, which remember I use my capital L for total angular momentum, would be the sum of L sub alphas. I'm going to go ahead and make that very clear. Alpha equals 1 to n r sub alpha cross p sub alpha. Okay? All right. So this is just our, I suppose that's worth a box. That's what we mean when we talk about total angular momentum of a system. So what else can we say about that? Let's see if that expression gives us anything else interesting. So I've got, maybe I want to think about the time rate of change of the total angular momentum of the system. That would be sum alpha plus 1 and r sub alpha cross p sub alpha dot. Now that's the only term. Remember, basically what I've done is I've taken a time derivative on both sides, but I remembered that taking the time derivative of r gives me dr dt crossed with p, which those two are in the same direction. V and p are always in the same direction. So that first term gave me 0. And so I just have the second term when I act with that time derivative left over. Okay, so it's r cross p dot. Okay. All right, so then, all right, so I already can see one important result from Newton's second law. I can go ahead and note that the time rate of change of momentum of the alpha particle is the net force on alpha. Okay, so that's a pretty good result. We're going to keep working and get one more result. All right. So I also have, let's go ahead and note that my forces on alpha, they could be from things that are external to my system of n particles, or they could be from things that are internal to my system of n particles, meaning some of the other of the n particles. So I'm going to write that sum, just sum over alpha, r sub alpha cross f external. And just to be clear, I'm not going to go ahead and put a net, although it should be external on alpha. All right, plus my sum over alpha. That's my sum over beta, which is not equal to alpha. It's the sum over all particles except for alpha. R sub alpha cross f internal on alpha. And now I can be clear that I mean by beta, where beta is another one of the particles. That's what an internal force would be on alpha by beta. Okay, that's fine, except it would be kind of nice if there's a nicer way to add these up. Well, so nice indeed that they turn out to be 0. So let's go ahead and do that. All right, oops, plus. So here I have sometimes beta is going to be greater than alpha, sometimes it's less than alpha. I'm going to go ahead and instead of doing that, I'm going to do half as much counting. So because I'm going to only count the times when beta was less than alpha. All right? So in that case, I have to, in my term, include both of those cases. So I've got r sub alpha crossed with r on alpha by beta. I'm sorry, f on alpha by beta, plus r sub beta crossed with f on beta by alpha. All right. So I'm not adding up all the different combinations of on 1 by 2, on 1 by 3, on 3. I'm just going to go through, I don't know if that makes sense, but there was sort of an array of here that I had to consider. I'm only considering half of it now, so that's why I have these two terms here, so no double counting. All right, so now what I have, okay, well, by Newton's third law, I know that the force on alpha by beta must be equal and opposite to the force on beta by alpha. So that allows me to write this as r sub alpha cross f alpha beta plus r sub beta cross negative f alpha beta. Also known as r sub alpha minus r sub beta crossed with f alpha beta. Okay, so if these internal forces are central in nature, meaning that they are either a push between two objects or a pull between two objects, and that is the assumption that we're making right now. First of all, there are two body forces, and there are pushes and pulls, all right? So if you ever decide to do QCD where there are three body forces, you'll have to rederive whatever the relationship would be. So we're going to have two body forces that are pushes or pulls, meaning they always act along the r hat direction of the object that's applying the force, meaning they're basically central in nature. Then this cross product will always give you 0 because they're parallel. All right? So we will just note 0 for central forces. Okay, pushes and pulls. All right, so in that case, then we just have to note that we have sum over alpha r sub alpha cross f external sub alpha. We only have to include external forces. Internal forces can be neglected because they always add up to 0. And if I look at this and I say, hey, you know what? The sum over all particles of the location of particle crossed with the external forces on that particle, the net external force on that particle, that is actually equal to the net external torque. All right, and these are the expressions that I wanted to get to because they show me that in the case that the net external torque on my system is 0, the total angular momentum of my system will be constant because the time rate of change of angular momentum will be 0. Let me write that out. If net external torque on my system is 0 for an n-particle, multi-particle system, then the time rate of change of the total angular momentum is also 0. And what that means is that the angular momentum will be constant. Okay, and that should be clear where that angular momentum that I'm talking about is the total angular momentum. Okay, so that's the conclusion that I wanted to draw. I'm going to put a box around it as well because it has a name. Oops. That is the principle of conservation of angular momentum. And what that means is that since L is equal to a constant, at all later times it will be equal to what it was at an initial time. So you can also write that. It's commonly written like so. L final equals L initial. Okay. So let's go ahead. Are there any questions about that? Cool. We'll be applying that in just a moment here. Before I apply that, I want to sort of loop back a little bit to this whole Kepler's second law discussion that I made here. 'Cause your book also includes another statement about Kepler's second law, and just for completeness, I want to go back and discuss that very quickly. So for a planet in orbit around a star, all right. And it doesn't matter. I mean, I can sort of draw that. That one's kind of near circular, but it doesn't matter if it's circular or not. I would have, you know, make a coordinate system here, maybe x, y. I'm looking at it sort of from above. I've got some planet located here, a distance r from the sun. It doesn't have to remain constant if it doesn't. And this angle relative to the positive x direction, I'll go ahead and call that phi. And in that case, the component, or the phi hat component of the velocity of that planet, which is the tangential velocity, which is what it will always move with, is going to be equal to r times d phi dt. This should remind you of calc-based intro. We've seen that before. And we call the time rate of change of phi the angular velocity, and we represent it with a lowercase omega. All right. So again, this is very similar to what we did with uniform circular motion in introductory physics. All right. So the next thing that I want to think about is my expression for the angular momentum of this planet about the sun. It's r cross p. And sure, I'll just talk about magnitude for right now. Okay, so that is equal to r times the component of p that is perpendicular to r, which we called p phi. You can always write a cross product that way as one of the vectors times the component of the other that's perpendicular to it. All right? Just a little reminder. Okay. So now I have r times m times this sort of v sub phi. I called it v tangential up above there. Okay. And I can make my substitution. Rm times r omega for that phi hat component of v. And I see that that is also equal to m r squared times omega. This is an expression that I have for the magnitude of the angular momentum of the planet. And I'm going to go ahead and put a little bit of a box around this and discuss it a little bit. All right. It means that the angular momentum is proportional to the angular velocity, and the constant proportionality in this case is mr squared because I'm treating the planet as a point particle, which is a very good approximation. I encourage you to always do, and we'll continue to do that. Okay, so in this expression, we will point out here that this constant of proportionality between angular momentum and angular velocity is defined as the moment of inertia and is represented by capital letter I. All right. For a point particle, or something that you want to treat as a point particle, the expression will just be mr squared, where r is the distance from the origin that we're thinking about. All right. Also, if I had multiple particles, maybe I wanted to find the total angular momentum associated with the whole solar system, I'd have to add up for each particle m sub I r sub I squared. That's fine. So that's for this expression here. I'm sure you guys remember this was just for a single particle, or something that can be well approximated as a particle. This is for multiple particles. I'll call it n particles. You know, assuming that this sum goes from 1 to n. All right. And last but not least, if I had a continuum of mass distribution instead of point particles, I would need to consider, instead of summing, I'd need to consider integrating over each increment of mass, which would be dm. It's r squared times that increment of mass. And so this would be the expression for a continuous mass distribution. Continuous mass distribution. Okay. We are going to do a whole lot more with this last expression in chapter 10, so just put a pin in that for right now. Everything we're going to do for this chapter is going to include either a point particle or multiple point particles. Okay? So we'll worry about this puppy. More on that in chapter 10. Okay. So, another thing that I should probably point out is that I wrote this not as a vector relationship, but I should consider it as a vector relationship. So I'm going to go ahead and note that if I did want to think about the single particle's angular momentum as a vector, I would have to also have a vector expression on this side. Clearly the angular velocity, just right there in its name, should be treated as a vector quantity. But what is the direction associated with that? In this case, if I have d phi dt is positive, then the motion is confined in the xy plane, but the direction associated with that motion is going to be the positive z direction, which is the out of the page direction. Because when you want to describe the direction of rotation, you describe it by the axis about which it's rotating, and you use your right hand to pick a direction on that. Are we all okay on that? All right. So it's rotating about the z-axis, so that's why this would be about the z-axis. And on the left-hand side, the reason that that would be about the z-axis is because we're thinking about r cross p here. R cross p, yeah, clearly that's going to be also associated with the positive z direction. So this would be the actual vector equality. And this can be also stated as a definition of, really it's definition of moment of inertia, but it's a statement, it's an expression for angular velocity for an extended object. Okay. Things to know. Since we're not going to be calculating these moments of inertia for our continuous mass distributions, now and then we're going to have continuous mass distributions. So I would like for you to know that I is equal to 1/2 mr squared for a uniform disk. So what I mean by that is that you've got something like this, you know, radius here of capital R, total mass m, and this is moment of inertia for rotation about its axis. Also, we have I equals 2/5 mr squared. This is for a uniform solid sphere. Also rotating about its axis, so this whole sphere is rotating. Okay. All right. And for now, we're just going to use our short-term memory to know what those are, or to look in our notes, because we are not going to learn, we're not going to actually derive them until chapter 10. All right. That's page 2 for today. Okay. So let's do an example. This is going to be the example from your textbook. Let me quickly outline it for you. I'm going to have a collision of a lump of putty and a turntable. Okay. All right. So I'm going to have, let me just sort of draw a picture of the situation here instead of writing out all these words. I've got this sort of circular turntable here. I'm going to kind of choose, have the origin for this system be at the center there. So this is the x-axis, this is the y-axis. All right. The turntable is going to have a radius of capital R and a total mass of m. So it's a total mass of m, and initially it is at rest, so it's not rotating. But in theory, it's kind of like some sort of a turntable. Maybe it's one of those that's used for clay modeling, I don't know, something like that. But it's free to rotate about its axis without friction. And so what I'm going to do, I should notice that, write that as well. Turntable has a frictionless axle. Okay. So what I'm going to do is I'm going to imagine, so I'm looking at this from above, I've got this turntable, and I'm going to imagine throwing a lump of putty, like so that it comes right in and splats and sticks to the turntable at some later time, but initially it's just being thrown. And this distance here between the line of velocity of the putty and the center of the turntable is B. And the mass of the lump of putty, we'll use a lowercase m to represent that. And it is thrown with a velocity v whose magnitude is lowercase v. All right? Okay, so that's the situation. And so after the putty collides with the turntable, later on, I'll have this situation where I now have this turntable that is rotating with this piece of putty stuck to the outside of it with some angular velocity, which we'll call omega final. All right. So the question is to find omega final. And I'll give you a moment to work on that before I start working. Did anybody get a solution yet? It can just be in terms of the different variables that we've already your neighbors. If you need to form groups, form groups. Logan's in a better place than you. Talk to Logan. That's very good. Yeah, I know, right? That's what I want. Then apply it. Okay, all right. So I'll go ahead and work it out. So the first thing that we need to do is think about what we would like to sort of apply here. What's the thing that comes to mind for you with this problem? Conservation of angular momentum, correct. That's what should come to mind. All right, so in that case, I'm going to go ahead and write. With these, I sometimes write them L initial equals L final, and I put initial stuff in it. I don't know, it makes sense to me. But anyway, so this is going to be conservation of angular momentum. But we need to think about how that could work. Is angular momentum of the turntable conserved? It's a simple question. It's not, right? No. No, no, no. Okay. So how do I get to apply this? Well, remember the time rate of change of a total system's angular momentum is equal to the net external torque. So what is it that changes the turntable's angular momentum? The putty. So if I include the putty, then that would be an internal force and an internal torque, and that would not I would still get to say my conservation, my angular momentum would be conserved for my putty plus turntable system. And indeed, that's exactly what I'm going to have to do. Okay. So I have to define my system as consisting of a turntable and putty. And you can imagine I'm either looking at it from above, that gravity wouldn't be affecting this component, or maybe this happens in outer space. I don't know. Either way, I'll get the same result. All right. So now I'm ready to go ahead and plug in. I've got a turntable. So initially I have I of the turntable times omega initial. Oh, you know what I'm going to do? Let me just note that all these angular momenta are about the z-axis, where the z-axis is out of the page because I have a right-handed coordinate system. All right, then I get away from the vector equation. All right, so then I've got I of the turntable times omega initial of the turntable, which we noted was 0, plus, and I'm going to let you guys complete that line. On both the left-hand side and the right-hand side of the equal sign. All right. So I have here R cross P, magnitude. So, and that is equal to I of the turntable plus I of putty, because then they're rotating together at some omega final. All right, so now I need to think about this R cross P business here. R, my origin for this problem, is the center of the turntable. So R is my vector that extends from there to the location of the center of that putty, of the lump of putty. So there's my R vector. And V is here. Now, if I want their cross product, that could be equal to the magnitude of one of the vectors times the component of the other vector perpendicular to that one. All right? So I'm going to write this as the magnitude of the second vector, which is MV, times the component of R that is perpendicular to that vector. So MV is here along this line. What's the component of R perpendicular to V? B. All right. Okay, and that's my initial angular momentum of my system. That will be equal to the final rotational inertia. So I've got rotational inertia of my turntable. It is a uniform disk, so, and it's a solid uniform disk, so it's 1/2 times mr squared. And now my putty is like just a little thing stuck to the outside of that disk. So I'm going to treat it as a point particle stuck to the outside. So it's going to have m, remember from before, if you have a point particle, it's just mr squared, where r is the distance from the origin. And in this case, that r remains equal to the radius of the turntable because it sticks there at the radius. You guys all right with that? Okay. Times omega final. So my expression for omega final is, and let me make sure that I don't have any errors. Looks good. That B value times the mass of the putty times the initial velocity of the putty divided by, sure, I can simplify that just a little bit, 1/2 m plus lowercase m. I'm going to pull out the capital R squared. Just put it in my denominator and make it look a little bit prettier and more simplified. And that's my answer. So the only trick here was to figure out how you have to define the system such that you can use conservation of angular momentum. The putty exerts a force on the turntable and back and vice versa. So I need to make the system include both of those so those internal forces will not be needed. All right. So, yeah, angular momentum about the center of mass. Well, I'll tell you what, I could power through and finish it. Should we finish the chapter? You guys have homework due on Friday, correct? I feel like your brains are full. So we'll just call it a day there. And we'll finish my 1 page of notes before the chapter is done, one little thing, at the start of next time. Go work on your homework and I'll see you next time. And like I said, I forgot to bring those graded things. I will bring those next time. And I also have Darcy's, you're the only one that didn't pick up your test, so I have your test as well. I left those in my office, so come to my office and get that.
Can we do it right now or Friday?
That would be great. May as well.
Last minute studying if you yep.
One less thing for me to have to remember for Friday. All right. Let me shut this down real quick.